Welcome students on today's lecture on design of water tank. So in the previous class we were designing a circular water tank with fixed base and free top. So let us see the data once again. So we were solving this question wherein the capacity was 4 lakh liters, depth of water was 4 meters and free board was 200 mm. Then the permissible tensile stress in concrete was 1.2 Newton per mm square and direct tension was 100 Newton per mm square. Okay, then we decided the dimension and the diameter worked out to be 11.5 meter. And we also decided the thickness of walls and the base slab and we took it as 200 mm. Now yesterday we were discussing about the next parameter, that is fourth parameter. In this there is bending moment, ring tension and ring shear. Now let us see in the code book. So as discussed yesterday, in this code book IS 3370 part 4, there are design tables. And yesterday we discussed the clause number 3. So let us go to the clause number 3. So here the clause number 3 deals with the cylindrical tanks, that is nothing but the circular water tank. Now in this 3.1 is nothing but how to calculate ring tension, movements in the walls as well as the shear. So we discussed about the different kind of conditions. So the first condition was wall with fixed base, free top and subjected to triangular load. So the details are given in this clause 3.1.1 and this is how the diagrams look like. So in figure 3, so wall with fixed base, free top subjected to triangular load. Now our numerical, if you see, it is a circular water tank, okay, with the fixed base and top nothing is there, so it is a free top. And here the water is placed, so obviously this will create a pressure on the walls and this pressure will be maximum at the bottom and minimum at this junction. So we will consider it as a triangular load. So this is a condition which we have to solve for. So we have to calculate the ring tension, movement and the shear walls for the circular tanks with fixed base, free top and subjected to triangular load. So how to calculate? They have given it. So here you can see the ring tension at various height of the wall of cylindrical tank fixed at base, free at top and subjected to triangular load are given in table number 9. That means what? We have to make the use of table number 9 to calculate ring tension. Then movements, that is bending moments. So bending moments in the cylindrical wall fixed at base, free at top and subjected to triangle load are given in table number 10. So we have to calculate bending moment according to the table number 10. Coefficient of for shear at the base of cylindrical wall are given in table number 11. So ring tension has to be computed according to table number 9. Movement are to be calculated according to table number 10 and shear is to be calculated according to the table number 11. So if you go here, the fourth is bending moment, ring tension and ring shear. So these are to be computed according to the table number 9, 10 and 11. Okay, and apart from this we discussed other conditions also, like the others are walls with hinged base and free top subjected to triangular load. Then we had walls with hinged base, free top and subjected to trapezoidal load. Now this, as discussed yesterday, this is a trapezoidal load because we have a triangular plus uniformly distributed load. This is due to the combined effect of the pressure. Then we also have walls with shear applied at the top. You can see here the shear is applied at the top as there is a fixed, not a free top but fixed top. Then walls with shear applied at the base. So this is how the shear is applied at the base. Then walls with movement applied at the top. So walls with movement applied at the top. So this is how to be calculated the different conditions. Now our condition is nothing but a cylindrical water tank with free top, fixed base and subjected to triangular load. So we have to solve according to the clause number 3.1.1. So just let us take the 3.1 and 3.1.1. So this is the figure for it. Okay, now let us go to the table. So let us calculate the first part. So the first part is, you can see here. So let us see. So we have calculated something called as h square divided by dt. Now from where did it come from? It came from the code book. So let us see there. So we'll go to the table. So here you can see the table 1 is for movement coefficient for individual walls, panels, top and bottom hinged. So this is not the component. Table 2 is also not used for this because we are having free top and fixed bottom. So they are already given the table number. So we have to go to the table number 9, 10 and 11. So let us go to the table number 9, 10 and 11. So this is table 6. So this is table 7, table 8 and table 9. Okay, here we have to go. So you can see here, so tension in the circular ring wall, that is circular water tank, fixed base, free top and subjected to triangle load. Now our diagram is the same, circular water tank with fixed base, free top, okay, and subjected to triangle load. So this is the table number 9. According to this, we have to calculate the tension in the circular ring wall. Okay, and that tension T is given by coefficient into W into H into R, where the diagram gives the component. So R, you can see R is nothing but the radius. Okay, and also W into H is given, so density into the height, D is diameter and H is the total height. Now here you can see what is the table about. So h square divided by dt, and here is the coefficient at the points which you have to compute. Note is given where omega is density of liquid. Note is given positive side indicates tension, that means positive side indicates tension. So we have to calculate the component h square divided by dt, where h is nothing but the total height of the wall, d is nothing but the diameter of the circular water tank, and t is the thickness of the tank walls. So let us compute. So h square divided by dt. So the height of the wall is 4.2 meter. So here 4.2 square divided by diameter is 11.5 meter. So diameter is 11.5 meter and thickness of the wall is 200 mm. So 0.2. So it is working out to be 7.66. So we round it out to 8. Now let us calculate the maximum bending moment. So the maximum bending moment will be got from referring table number 10. Okay, so as you can see, for bending moment, ring tension and ring shear, we have to compute according to the table number 9, 10 and 11. Now, however, we are referring to the table number 9, let us compute. So you can see the table number 9 gives tension coefficient into omega h into r. So let us come one by one. So let us calculate the maximum bending moment will be got after referring table number 10. Now what is table number 10? This is the table. So this is the calculation of bending moment in the cylindrical wall with fixed base, free top and subjected to triangle load. So what is required? H square divided by dt, which we have computed. And how we can get the moment? Moment is nothing but whatever coefficient we get into omega into h cube kg meter per meter. Okay, so where h is the height of the tank wall. So let us see here. So IS, according to the IS 3370 part 4, page number 35, for 8, h square divided by dt is 8 and 1h. So you can see, so h square divided by dt is 8 and 1h is this. So what is the component? Minus 0.0146. So this is the component, minus 0.0146. So this is for h square divided by dt for 8 and 1h, the value is minus 0.0146. Here you can see the omega is the density of liquid and positive side indicates tension on the outside. So how to calculate movement? Movement is equal to coefficient into omega h cube. So here you can see maximum coefficient of movement for bending moment, we got it as 0.0146, tension on the water side. here you can see it is given the tension on the outside if positive. Now our value is negative, so the value is nothing but tension on the water side. So hoop tension coefficient according to the page number 34. Now let us even check the hoop tension. So that is ring tension. So hoop tension according to the table number 34, table number 9 IS 3370 part 4 for 0.6 H plus. So this is at 0.6 H from the top. So this is from the top coefficient. So ours H square divided by dt is 8 and 0.6 H. So the value is plus 0.575. Again here positive sign indicates tension, that means it is a tension, and omega is density of the liquid. So this is nothing but tension is got by the formula coefficient into omega H into R. So here it is equal to. So maximum bending moment, this is got from table number 10, maximum bending moment, which is coefficient into omega H cube, which is coefficient into omega H cube kg meter per meter. So coefficient we have computed, that is minus 0.0416. So minus 0.0146 into density of liquid 9.81 into height is 4.2 cube, which is working out to be 10.61 kilonewton meter per meter. Then let us also compute the shear. So shear is given in table number 11. So shear at the base of the cylindrical wall. So how we get shear? Shear V is equal to coefficient into. Now here are three conditions given. One is for triangular load, one is for rectangular load, and moment at the base. So we are calculating for triangular. So coefficient into omega h square into kg. H square divided by dt we are already calculated, which is 8, and we have a triangular load with fixed base. Hence the value is plus 0.174. Where positive sign indicates the shear is acting inwards. So this is positive, so it is acting inwards. So let us see. So maximum shear is given by coefficient into omega into h square. So 0.174 into 9.81 into 4.2 square, which is working out to be 30.11 kilonewton. This is at the base. So the maximum bending moment working out is 10.61 kilonewton meter, and maximum shear working out is 30.11 kilonewton. For maximum bending moment we have referred table number 10. For maximum shear we have referred table number 11, and maximum ring tension we have referred table number 9. So let us see. So let us go to the table number 9. So this is given by tension, hoop tension, coefficient into omega h into r kg per meter. So it is given by coefficient into omega h into r. So coefficient we already calculated and noted down, that is 0.575 positive. So you can see for 8 and 1h, so it is nothing but 0.68, 0.68, 0.575. So it is 0.575 into omega is 9.81 into height is 4.2, and the diameter is 11.35, I think so. So diameter is 11.5. So 11.5 divided by 2 will give us the radius, which is 6.25. So that hoop tension is working out to be 148.069 kilonewton. So we computed in the fourth step bending moment, ring tension, and ring shear. The bending moment according to the table number 10, which is working out to be 10.61 kilonewton meter. Then ring tension, which is given by table number 9. So ring tension, maximum ring tension is T is equal to 148.069, and the ring shear. So we got the ring shear, that is maximum shear according to table number 11, which is working out to be 30.11 kilonewton at the base. So this is how we have to compute the bending moment and the ring tension and the ring shear at the base of the wall. So next we have to design the section. So this we will see in the next class. So just we can see that, remember once again, how do we decide the table number? Here they have given the title. So it is a circular water tank with fixed base and free top. So depending upon this condition, a particular table has to be referred. So we are dealing with circular water tank with fixed base and free top and triangular load. So hence table number 9 is used for tension, and this has to be computed and this has to be taken into account. Similarly, movement according to table number 10 and shear according to table number 11. Now these are for circular water tank, and for free top and fixed base. If some other condition, like you can see here, shear at the edge of the walls, free at top and hinge at bottom. So even there are different conditions. So depending upon the type of condition of our water tank, we have to select the appropriate table number from the codebook IS 3370 part 4, and we have to design. So this is for today. Thank you.